Some of the major unsolved problems in physics are theoretical, meaning that existing theories seem incapable of explaining a certain observed phenomenon or experimental result. The others are experimental, meaning that there is a difficulty in creating an experiment to test a proposed theory or investigate a phenomenon in greater detail. Is the theory of cosmic inflation correct, and, if so, what are the details of this epoch? What is the hypothetical inflaton field giving rise to inflation? If inflation happened at one point, is it self-sustaining through inflation of quantum mechanical fluctuations, and thus ongoing in some extremely distant place? Horizon problem. Why is the distant universe so homogeneous, when the Big Bang theory seems to predict larger measurable anisotropies of the night sky than those observed? Cosmological inflation is generally accepted as the solution, but are other possible explanations such as a variable speed of light more appropriate? Electroweak horizon problem. Why aren't there obvious large-scale discontinuities in the electroweak vacuum if distant parts of the observable universe were causally separate when the electroweak epoch ended? Standard cosmological inflation models have inflation cease well before electroweak symmetry breaking occurs, so it is not at all clear how inflation could prevent such discontinuities. Future of the universe. Is the universe heading towards a big freeze, a big rip, a big crunch, or a big bounce? Or is it part of an infinitely recurring cyclic model? Gravitational wave. Can gravitational waves be directly detected? Baryon asymmetry. Why is there far more matter than antimatter in the observable universe? Cosmological constant problem. Why does the zero-point energy of the vacuum not cause a large cosmological constant? What cancels it out? Estimated distribution of dark matter and dark energy in the universe. Dark matter. What is the identity of dark matter? Is it a particle? Is it the lightest superpartner, LSP? Do the phenomena attributed to dark matter point not to some form of matter, but actually to an extension of gravity? The results obtained by the Large Underground's Xenon Lux experiment that took place in 2013 at Sanford Underground Research Facility place a lower bound on the LSP mass. At this point, light supersymmetric particles that are the main candidate for dark matter in the lower mass sector are excluded with 90% confidence. The log-log plot of dark energy density and material density versus scale factor. The two straight lines intersect at current epoch. Dark energy. What is the cause of the observed accelerated expansion, de Sitter phase, of the universe? Why is the energy density of the dark energy component of the same magnitude as the density of matter at present, when the two evolve quite differently over time? Could it be simply that we are observing at exactly the right time? Is dark energy a pure cosmological constant, or are models of quintessence such as phantom energy applicable? Dark flow. Is a non-spherically symmetric gravitational pull from outside the observable universe responsible for some of the observed motion of large objects such as galactic clusters in the universe? Ecliptic alignment of CMB anisotropy. Some large features of the microwave sky at distances of over 13 billion light-years appear to be aligned with both the motion and orientation of the solar system. Is this due to systematic errors in processing, contamination of results by local effects, or an unexplained violation of the Copernican principle? Shape of the universe. What is the three-manifold of co-moving space, i.e., of a co-moving spatial section of the universe, informally called the shape of the universe? Neither the curvature nor the topology is presently known, though the curvature is known to be close to zero on observable scales. The cosmic inflation hypothesis suggests that the shape of the universe may be unmeasurable, but, since 2003, Jean-Pierre Lamina et al. And other groups have suggested that the shape of the universe may be the Poincare dodecahedral space. Is the shape unmeasurable, the Poincare space, or another three-manifold? Quantum gravity. Vacuum catastrophe. Why does the predicted mass of the quantum vacuum have little effect on the expansion of the universe? Quantum gravity. Can quantum mechanics and general relativity be realized as a fully consistent theory, perhaps as a quantum field theory? Is space-time fundamentally continuous or discrete? Would a consistent theory involve a force mediated by a hypothetical graviton, or be a product of a discrete structure of space-time itself, as in loop quantum gravity? Are there deviations from the predictions of general relativity at very small or very large scales, or in other extreme circumstances that flow from a quantum gravity theory? Black holes, black hole information paradox, and black hole radiation. Do black holes produce thermal radiation, as expected on theoretical grounds? Does this radiation contain information about their inner structure, as suggested by gauge gravity duality, or not, as implied by Hawking's original calculation? If not, and black holes can evaporate away, what happens to the information stored in them? Quantum mechanics does not provide for the destruction of information. Or does the radiation stop, at some point leaving black hole remnants? Is there another way to probe their internal structure somehow, if such a structure even exists? Extra dimensions. Does nature have more than 4 space-time dimensions? If so, what is their size? Are dimensions a fundamental property of the universe, or an emergent result of other physical laws? Can we experimentally observe evidence of higher spatial dimensions? The cosmic censorship hypothesis, and the chronology protection conjecture. Can singularities not hidden behind an event horizon, known as naked singularities, arise from realistic initial conditions, or is it possible to prove some version of the cosmic censorship hypothesis of Roger Penrose which proposes that this is impossible? Similarly, will the closed time-like curves which arise in some solutions to the equations of general relativity, and which imply the possibility of backwards time travel, be ruled out by a theory of quantum gravity which unites general relativity with quantum mechanics, as suggested by the chronology protection conjecture of Stephen Hawking? Locality. Are there non-local phenomena in quantum physics? If they exist, are non-local phenomena limited to the entanglement revealed in the violations of the Bell inequalities, or can information and conserved quantities also move in a non-local way? Under what circumstances are non-local phenomena observed? What does the existence or absence of non-local phenomena imply about the fundamental structure of space-time? How does this relate to quantum entanglement? How does this elucidate the proper interpretation of the fundamental nature of quantum physics? High-energy physics/particle physics. A simulation of how a detection of the Higgs particle would appear in the CMS detector at CERN. Higgs mechanism. Are the branching ratios of the Higgs boson consistent with the Standard Model? Is there only one type of Higgs boson? Hierarchy problem. Why is gravity such a weak force? It becomes strong for particles only at the Planck scale, around 1019 GeV, much above the electroweak scale, 100 GeV, the energy scale dominating physics at low energies. Why are these scales so different from each other? What prevents quantities at the electroweak scale, such as the Higgs boson mass, from getting quantum corrections on the order of the Planck scale? Is the solution supersymmetry, extra dimensions, or just anthropic fine-tuning? Magnetic monopoles. Did particles that carry magnetic charge exist in some past, higher energy epoch? If so, do any remain today? Paul Dirac showed the existence of some types of magnetic monopoles would explain charge quantization. Proton decay and spin crisis. Is the proton fundamentally stable? Or does it decay with a finite lifetime, as predicted by some extensions to the Standard Model? How do the quarks and gluons carry the spin of protons? Supersymmetry. Is space-time supersymmetry realized at TeV scale? If so, what is the mechanism of supersymmetry breaking? Does supersymmetry stabilize the electroweak scale, preventing high quantum corrections? Does the lightest supersymmetric particle, LSP, comprise dark matter? Generations of matter. Why are there 3 generations of quarks and leptons? Is there a theory that can explain the masses of particular quarks and leptons in particular generations from first principles, a theory of Yukawa couplings? Electroweak symmetry breaking. What is the mechanism responsible for breaking the electroweak gauge symmetry, giving mass to the W and Z bosons? Is it the simple Higgs mechanism of the Standard Model, or does nature make use of strong dynamics in breaking electroweak symmetry, as proposed by Technicolor? Neutrino mass. What is the mass of neutrinos, whether they follow Dirac or Majorana statistics? Is mass hierarchy normal or inverted? Is the CP violating phase zero? Asymptotic confinement. Why has there never been measured a free quark or gluon, but only objects that are built out of them, like mesons and baryons? How does this phenomenon emerge from QCD? Strong CP problem and axions. Why is the strong nuclear interaction invariant to parity and charge conjugation? Is Pache-Equin theory the solution to this problem? Anomalous magnetic dipole moment. Why is the experimentally measured value of the muon's anomalous magnetic dipole moment, muon G2, significantly different from the theoretically predicted value of that physical constant? Proton size puzzle. What is the true charge radius of the proton? Astronomy and astrophysics. Relativistic jet. The environment around the AGN, where the relativistic plasma is collimated into jets which escape along the pole of the supermassive black hole. Accretion disk jets. Why do the accretion disks surrounding certain astronomical objects, such as the nuclei of active galaxies, emit relativistic jets along their polar axes? Why are there quasi-periodic oscillations in many accretion disks? Why does the period of these oscillations scale as the inverse of the mass of the central object? Why are there sometimes overtones, and why do these appear at different frequency ratios in different objects? Coronal heating problem. Why is the Sun's corona atmosphere layer so much hotter than the Sun's surface? Why is the magnetic reconnection effect many orders of magnitude faster than predicted by standard models? Diffuse interstellar bands. What is responsible for the numerous interstellar absorption lines detected in astronomical spectra? Are they molecular in origin, and if so, which molecules are responsible for them? How do they form? Gamma ray bursts. How do these short-duration high-intensity bursts originate? Supermassive black holes. What is the origin of the M-sigma relation between supermassive black hole mass and galaxy velocity dispersion? How did the most distant quasars grow their supermassive black holes up to 10 circumflex 9 solar masses so early in the history of the universe? Observational anomalies. Rotation curve of a typical spiral galaxy, predicted A, and observed B. Can the discrepancy between the curves be attributed to dark matter? Kuiper cliff. Why does the number of objects in the solar system's Kuiper belt fall off rapidly and unexpectedly beyond a radius of 50 astronomical units? Flyby anomaly. Why is the observed energy of satellites flying by Earth sometimes different by a minute amount from the value predicted by theory? Galaxy rotation problem. Is dark matter responsible for differences in observed and theoretical speed of stars revolving around the center of galaxies, or is it something else? Supernovae. What is the exact mechanism by which an implosion of a dying star becomes an explosion? Ultra-high energy cosmic ray. Why is it that some cosmic rays appear to possess energies that are impossibly high, the so-called OMG particle, given that there are no sufficiently energetic cosmic ray sources near the Earth? Why is it that, apparently, some cosmic rays emitted by distant sources have energies above the Greisen-Zatsepin-Kuzmin limit? Rotation rate of Saturn. Why does the magnetosphere of Saturn exhibit a slowly changing periodicity close to that at which the planet's clouds rotate? What is the true rotation rate of Saturn's deep interior? Origin of magnet or magnetic field. What is the origin of magnet or magnetic field? Space roar. Why is space roar 6 times louder than expected? What is the source of space roar? Age-metallicity relation in the galactic disk. Is there a universal age-metallicity relation in the galactic disks? A sample of 229 nearby thick disk stars has been used to investigate the existence of an age-metallicity relation, AMR, in the galactic thick disk. The results indicate that there is indeed an age-metallicity relation present in the thick disk. Nuclear physics. The island of stability and the proton versus neutron number plot for heavy nuclei. Quantum chromodynamics. What are the phases of strongly interacting matter, and what roles do they play in the cosmos? What is the internal landscape of the nucleons? What does QCD predict for the properties of strongly interacting matter? What is the role of gluons and gluon self-interactions in nucleons and nuclei? What determines the key features of QCD, and what is their relation to the nature of gravity and spacetime? Do glue balls exist? Do gluons acquire mass dynamically despite having a zero rest mass within hadrons? Does QCD truly lack CP violations? Nuclei and nuclear astrophysics. What is the nature of the nuclear force that binds protons and neutrons into stable nuclei and rare isotopes? What is the origin of simple patterns which in complex nuclei? What is the nature of exotic excitations in nuclei at the frontiers of stability and their role in stellar processes? What is the nature of neutron stars and dense nuclear matter? What is the origin of the elements in the cosmos? What are the nuclear reactions that drive stars and stellar explosions? Plasma physics and fusion power. Fusion energy may potentially provide power from abundant resource, e.g., hydrogen, without the type of radioactive waste that fission energy currently produces. However, can ionized gases, plasma, be confined long enough and at a high enough temperature to create fusion power? What kinds of advances in material science must be made? Atomic, molecular and optical physics. Hydrogen atom. What is the solution to the Schrödinger equation for the hydrogen atom in arbitrary electric and magnetic fields? Muonic hydrogen. Is the radius of muonic hydrogen inconsistent with the radius of ordinary hydrogen? Laser cooling. Can molecules be cooled by laser cooling, as is now done to atoms? Condensed matter physics. A sample of a cuprate superconductor, specifically BSCCO. The mechanism for superconductivity of these materials is unknown. High-temperature superconductors. What is the mechanism that causes certain materials to exhibit superconductivity at temperatures much higher than around 25 Kelvin? Is it possible to make a material that is a superconductor at room temperature? Amorphous solids. What is the nature of the glass transition between a fluid or regular solid and a glassy phase? What are the physical processes giving rise to the general properties of glasses and the glass transition? Cryogenic electron emission. Why does the electron emission in the absence of light increase as the temperature of a photomultiplier is decreased? So no luminescence. What causes the emission of short bursts of light from imploding bubbles in a liquid when excited by sound? Dated info. Turbulence. Is it possible to make a theoretical model to describe the statistics of a turbulent flow, in particular, its internal structures? Also, under what conditions do smooth solutions to the Navier-Stokes equations exist? This problem is also listed as one of the Millennium Prize problems in mathematics. Alphinic turbulence in the solar wind and the turbulence in solar flares, coronal mass ejections, and magnetospheric substorms are major unsolved problems in space plasma physics. Topological order. Is topological order stable at non-zero temperature? Equivalently, is it possible to have three-dimensional self-correcting quantum memory? Fractional Hall effect. What mechanism explains the existence of the state in the fractional quantum Hall effect? Does it describe quasi-particles with non-abelian fractional statistics? Bose-Einstein condensation. How do we rigorously prove the existence of Bose-Einstein condensates for general interacting systems? Liquid crystals. Can the nematic systematic A phase transition in liquid crystal states be characterized as a universal phase transition? Semiconductor nanocrystals. What is the cause of the non-parabolicity of the energy size dependence for the lowest optical absorption transition of quantum dots? Electronic band structure. Why can band gaps not accurately be calculated? Biophysics. Stochasticity and robustness in noise and gene expression. How do genes govern our body, withstanding different external pressures and internal stochasticity? Certain models exist for genetic processes, but we are far from understanding the whole picture, in particular in development, where gene expression must be tightly regulated. Quantitative study of the immune system. What are the quantitative properties of immune responses? What are the basic building blocks of immune system networks? What roles are played by stochasticity? Homochirality. What is the origin of the preponderance of specific enantiomers in biochemical systems? Other problems. Entropy, arrow of time. Why did the universe have such low entropy in the past, resulting in the distinction between past and future, and the second law of thermodynamics? Why are CP violations observed in certain weak force decays, but not elsewhere? Are CP violations somehow a product of the second law of thermodynamics, or are they a separate arrow of time? Are there exceptions to the principle of causality? Is there a single possible past? Is the present moment physically distinct from the past and future, or is it merely an emergent property of consciousness? Why does time have a direction? Interpretation of quantum mechanics. How does the quantum description of reality, which includes elements such as the superposition of states and wave function collapse or quantum decoherence, give rise to the reality we perceive? Another way of stating this is the measurement problem. What constitutes a measurement which causes the wave function to collapse into a definite state? Unlike classical physical processes, some quantum mechanical processes, such as quantum teleportation arising from quantum entanglement, cannot be simultaneously local causal and real, but it is not obvious which of these properties must be sacrificed, or if an attempt to describe quantum mechanical processes in these senses is a category error. That doesn't even make sense to talk about if one properly understands quantum mechanics. Theory of everything, granunification theory. Is there a theory which explains the values of all fundamental physical constants? Is the theory string theory? Is there a theory which explains why the gauge groups of the Standard Model are, as they are, why observed spacetime has 3 spatial dimensions, and 1 dimension of time, and why all laws of physics are, as they are? Do fundamental physical constants vary over time? Are any of the particles in the Standard Model of particle physics actually composite particles too tightly bound to observe as such at current experimental energies? Are there fundamental particles that have not yet been observed, and if so, which ones are they, and what are their properties? Are there unobserved fundamental forces implied by a theory that explains other unsolved problems in physics? Yang-Mills theory. Given an arbitrary compact gauge group, does a non-trivial quantum Yang-Mills theory with a finite mass gap exist? This problem is also listed as one of the Millennium Prize problems in mathematics. Physical information. Are there physical phenomena, such as wave function collapse, or black holes, which irrevocably destroy information about their prior states? How is quantum information stored as a state of a quantum system? Quantum computation. Is David Deutsch's notion of a universal quantum computer sufficient to efficiently simulate an arbitrary physical system? Dimensionless physical constant. At the present time, the values of the dimensionless physical constants cannot be calculated. They are determined only by physical measurement. What is the minimum number of dimensionless physical constants from which all other dimensionless physical constants can be derived? Are dimensionful physical constants necessary at all? Problems solved in recent decades. Ball lightning. 2014. In January 2014, scientists from Northwest Normal University in Lanzhou, China, published the results of recordings made in July 2012 of the optical spectrum of what was thought to be natural ball lightning made during the study of ordinary cloud ground lightning on China's Qinghai Plateau. At a distance of 900 m, 3,000 feet, a total of 1.64 seconds of digital video of the ball lightning and its spectrum was made from the formation of the ball lightning after the ordinary lightning struck the ground, up to the optical decay of the phenomenon. It is now believed that ball lightning has vaporized silicon in the soil, that then rapidly oxidizes in the atmosphere. Hipparcos anomaly, 2012. The actual distance to the Pleiades, the high-precision parallax collecting satellite, Hipparcos, measured the parallax of the Pleiades and determined a distance of 385 light-years. This was significantly different from other measurements made by means of actual to apparent brightness measurement, or absolute magnitude. The anomaly was due to a systematic bias in the Hipparcos data. When it comes to star clusters, the Hipparcos results for clusters are consistently closer than they should be. Not in citation given. Pioneer anomaly, 2012. The section's factual accuracy is disputed. January 2014, there was a deviation in the predicted accelerations of the Pioneer spacecraft as they left the solar system. It is believed that this is a result of previously unaccounted for thermal recoil force. Long-duration gamma-ray bursts, 2003. Long-duration bursts are associated with the deaths of massive stars in a specific kind of supernova, like event commonly referred to as a collapsar. However, there are also long-duration GRBs that show evidence against an associated supernova, such as the swift event GRB 060614. Solar neutrino problem, 2002. Solved by a new understanding of neutrino physics, requiring a modification of the standard model of particle physics, specifically neutrino oscillation. Age crisis, 1990s. The estimated age of the universe was around 3 to 8 billion years younger than estimates of the ages of the oldest stars in our galaxy. Better estimates for the distances to the stars and the recognition of the accelerating expansion of the universe reconcile the age estimates. Quasars, 1980s. The nature of quasars was not understood for decades. They are now accepted as a type of active galaxy where the enormous energy output results from matter falling into a massive black hole in the center of the galaxy.